Okay, just think about how my AI is already, well, part of your day.
It really is everywhere.
Yeah, like song recommendations, the news you see. AI is kind of quietly shaping things, but
Yeah.
the big question is how we make it truly smart, adaptable, especially with all the different kinds of situations it runs into.
And that's exactly what we're digging into today. How do we get AI to learn well from all these different types of information? The paper we're looking at calls them heterogeneous environments.
Right,
And
heterogeneous.
this is super critical now as AI tackles really complex, messy, real-world problems.
Totally. That old idea, training AI on just one clean, uniform data set, that's kind of fading.
It really is.
Now, data set, well, it's messy. Comes from all over, each bit with its own quirks. And the really wild thing, the core finding from this paper we're discussing, Impossibility of Collective Intelligence
Mhm.
from May 2025, is that getting AI to learn collectively the way we sort of imagine it should, it might actually be impossible.
Impossible under, yeah, some
Yeah.
pretty reasonable assumptions. It sounds dramatic, but
Yeah. It does. But you're saying it's not just theory.
no, not at
Yeah.
all. If you want to really get a handle on AI's future, its potential and its limits, this paper is pretty essential reading. It cuts right to the chase about wanting AI that's capable and fair without getting bogged down. It highlights these unavoidable trade-offs.
Yeah, and what I found cool is how it borrows ideas from social choice theory.
Exactly. Like how groups make decisions, applying that to how machine learning algorithms work. That's a really neat angle.
So, our mission for this deep dive. Let's unpack that main argument. Why might collective intelligence be impossible? And crucially, what does that actually mean for the AI we're building day to day?
Okay, let's jump in.
So, first up,
Hmm.
this explosion of different data types in AI. The paper points out traditionally ML often assumed IID data, right?
Right. Identically and independently distributed, like drawing marbles from one single well-mixed bag. A nice, simple starting point.
But that's not the reality now.
Not anymore. The reality is these heterogeneous environments. Our data isn't one big blob. It's a collection of different data sets, each with its own signature, its own patterns, sometimes even collected differently.
And the paper gives some great examples where this pops up all the time.
Yeah, it does.
Like multitask learning AI doing several jobs at once, or domain generalization trained on one thing needs to work on something slightly different.
Or out-of-distribution generalization, that's another big one. Federated learning, too.
Right. Keeping data private on phones, but learning together, algorithmic fairness, making sure it works for everyone, and multimodal learning images, text, audio, all together.
Exactly. All those areas, they fundamentally grapple with data diversity.
And why is this happening? It's not just because, right?
No, the paper makes a good point. There are practical reasons. Privacy is huge, think federated learning or sensitive hospital data. Security matters. Equity is critical, hence the focus on fairness. And honestly, the world is just diverse. We can't expect and maybe shouldn't even want perfectly uniform data all the time.
Okay, so diverse data is the reality, and it's a challenge. Now, the paper shifts perspective, looking at machine learning almost like making choices. They call it a choice theoretic perspective.
Yeah, that's the interesting twist. It frames designing an ML algorithm as setting up a system to make choices. They talk about a learning structure like the blueprint.
The blueprint, okay.
It includes H, the hypothesis space, that's all the possible models the AI could learn. Then B, different collections or classes of those models. And A, the learning algorithm itself, which they frame as a choice correspondence.
Okay, choice correspondence. Break that down a bit for us. Still sounds a bit academic.
Think of it like this. You give the AI a menu of possible solutions. That's your hypothesis space. The choice correspondence is the rule it uses to pick the best ones from that menu based on the data.
So it's not necessarily finding the one perfect answer.
Right. It might select a small set of really good contenders, like
Yeah.
saying, out of these 100 options, these 5 look most promising based on what I've seen.
Gotcha. Like narrowing down the possibilities.
Exactly. And the paper puts this in a two-stage context. Model selection, first deciding the overall strategy, which models to even consider, which rulebook or algorithm to use. Then model training, where the chosen algorithm actually runs and picks the best models. It helps analyze the whole pipeline as a series of choices.
Okay, so learning is choosing. What makes an algorithm a good chooser? Or, as they say, rational?
So here they pull in ideas from economics, from rational choice theory. They argue a minimal requirement for a rational algorithm is internal consistency,
Internal consistency.
which breaks down into two properties, property alpha and property beta.
Okay, property alpha. What's the gist?
Property alpha is pretty intuitive. If an algorithm picks solution X when it has a big set of options, you should still pick solution X if you shrink the set of options as long as X is still available.
Example.
Okay, think about fitting curves to data points. Your algorithm can choose polynomials up to degree 10. It decides degree 5 is best. Now, if you restrict it to only choose up to degree 7, it should still pick degree 5, assuming that was its top choice before. It shouldn't suddenly jump to degree 7 just because the options changed slightly if 5 was already optimal.
Okay, that makes sense. If it was the best, it's still the best among fewer options. What about property beta?
Beta is a bit more subtle. Imagine the algorithm picks solutions X and Y as equally good from a small set of options. Now you give it a much bigger set of options. If X still looks like a good choice in this bigger set, then Y, which was just as good initially, should also still be considered a good choice.
So it's about consistency for things that were equally good.
Yeah, it's about ensuring that if adding more options doesn't disqualify one initially good choice, it shouldn't disqualify others that were equivalent to it, like maintaining fairness to those initial top contenders.
Right. And the paper says most standard ML algorithms kind of naturally follow these rules, like algorithms that minimize error.
Exactly. Things like empirical risk minimization, ERM, structural risk minimization, SRM, they often minimize some loss function. That optimization process usually leads to this kind of logical internal consistency. They satisfy alpha and beta.
Okay, so we have rational algorithms. How does this connect back to learning across different types of data?
This is where collective intelligence, or CI, comes in. In this AI context, the paper defines CI as the ability to learn successfully across those different heterogeneous environments we talked about.
The goal, basically.
Right. The idea is that by somehow combining insights from different sources, the AI gets smarter, more robust than just learning from one source alone.
And how do we model that combination process?
They introduce an aggregation function, let's call it F. Think of F as the rule or mechanism the algorithm uses to pull together information from all the different environments,
What kind of information?
specifically risk profiles.
Risk profiles. So how does the AI judge performance if the data is so varied?
Good question. A risk profile is basically a scorecard for each potential AI model. For Model A, the profile tells you its performance, say its error rate in environment 1, its error rate in environment 2, and so on for all the environments.
So every possible model gets a list of scores showing how well it does everywhere.
Precisely. A snapshot of its performance across the board.
Okay, so we've got these scorecards, these risk profiles, and the aggregation function takes all these profiles and decides which model is the overall best, considering all the environments.
You got it. Now, the crucial bit, the paper lays out principles that they argue any rational aggregation function for heterogeneous environments should follow. These seem pretty reasonable on the surface.
Okay, let's hear them. First one, Pareto optimality, PO.
Yep, Pareto optimality comes from economics. Basically, if Model A is strictly better than Model B in every single environment, like lower error everywhere, then the algorithm absolutely must choose Model A over Model B.
Seems obvious. If one's always better, pick it.
Right.
Hard to argue with that one. Next is IIH, independence of irrelevant hypotheses. IIH.
This says the choice between Model A and Model B should only depend on how A and B compare to each other across the environments. The presence or absence of some other model, Model C, shouldn't change whether A is preferred to B.
So adding a third wheel shouldn't mess up the comparison between the first two?
Exactly. The AVS-B comparison should stand on its own.
Okay. Third one, invariance restriction, IR. This one sounds a bit more technical.
It is, a little. IR means the algorithm's final choice shouldn't change if we apply certain consistent transformations to the risk scores within each environment, as long as those transformations don't change the underlying preference order within that environment.
Example.
Okay, suppose in environment 1, we measured error rates. Now, what if we decided to measure squared error rates instead? Or maybe add 5 to all error rates in that environment. As long as we do it consistently for all models in that specific environment, the relative ranking, which model is better than which within environment 1, doesn't change. IR says the algorithm's overall choice shouldn't change either, just because we rescale the numbers in one place.
So it needs to be robust to the units or scale we use in each separate environment, focusing on the relative performance.
Correct. It shouldn't be thrown off by arbitrary scaling choices in one dataset versus another. It should look at the real information.
Got it. And the last principle is collective intelligence itself, CI.
Yes, CI simply means the algorithm must actually use information from more than one environment. It can't just default to picking one environment and optimizing only for that one, ignoring all the others. That wouldn't be collective intelligence.
Okay. So, 4 principles. PO, pick the universally better one. IIH, choices are independent of irrelevant options. IR, robust to scaling within environments. And CI, use multiple environments. They all sound pretty good. Can we have them all?
And that is the core of the paper, the big reveal. They prove that no, you can't.
Seriously.
Seriously, no rational learning algorithm, one that satisfies internal consistency, alpha and beta, can simultaneously satisfy PO, IIH, IR, and CI, provided you have at least 2 different environments and at least 3 potential models to choose from.
Wow. Okay, so something has to give. We can't satisfy all those desirable properties at the same time. That's surprising.
It really is. And the implication is stark. They showed that the only way to satisfy PO, IIH, and IR simultaneously is to essentially become a dictator. The algorithm picks one environment and bases its entire decision on the risk profile from that single environment alone.
So it ignores all the others.
Completely.
Yeah.
It satisfies the first 3 rules, but it totally fails on collective intelligence. It doesn't learn collectively at all.
That's, yeah, pretty stark. If we insist on those seemingly sensible rules like PO, IIH, and IR, we end up with an algorithm that isn't actually doing what we wanted, learning from diverse sources.
It forces a trade-off. To achieve genuine CI, you must relax at least one of those other 3 conditions.
Okay, so this isn't just math theory. What does this impossibility mean out there in the real world for practical AI development?
Well, it sheds light on challenges we see all the time. Think about multi-source learning, domain generalization, multitask learning. Why is it often so hard to get a performance boost just by adding more data sets or tasks?
Yeah.
This theorem suggests there's a fundamental barrier if we implicitly stick to PO, IIH, and IR. Especially if our loss functions, how we measure error, aren't perfectly comparable across tasks. The paper does mention if losses are comparable, maybe you can drop IR, which helps.
Okay, so if the scoring is different across tasks, combining them rationally while respecting those other rules becomes mathematically difficult. What about algorithmic fairness?
That's another area. The theorem hints at why it might be hard to be truly fair across different groups if you strictly follow PO, IIH, and IR. You might end up implicitly favoring performance in one group, like optimizing for one environment, over others, even before you add explicit fairness constraints. It points to an inherent tension.
And federated learning, where data stays local.
For federated learning algorithms to work, to actually combine knowledge effectively from all those devices without violating privacy, they have to be violating at least one of PO, IIH, or IR. This highlights the unavoidable compromises involved in designing those systems.
And multimodal learning. Images, text, audio.
Yeah, the paper argues that's almost a perfect storm for this problem. How do you compare risk in an image task versus a text task? The units, the scales, what error even means is often fundamentally different. They call this informational incomparability.
Informational incomparability, that sounds like the root cause.
It seems to be. It's this core idea that often we just can't meaningfully compare performance improvements across totally different contexts. There's no universal yardstick.
Why not? What stops us?
It could be physical limits, like different sensors,
Yeah.
ethical reasons, how do you weigh an error's impact in healthcare versus entertainment, legal constraints, cultural differences affecting how an AI should behave, or just the sheer difference in the nature of the tasks.
Give me another concrete example.
Okay, a self-driving car. How do you compare the risk of a minor fender bender in slow city traffic versus the risk of misidentifying a sign on a high-speed highway? They're both errors, but the implications, the scales of risk are wildly different. Comparing them directly is really hard.
Or comparing a medical AI's performance in a rich hospital versus a poor one.
Exactly. The same accuracy percentage might mean something very different in terms of lives saved or resources used. They're informationally incomparable in some crucial ways.
So because we have this incomparability, that invariance restriction principle, IR, becomes important. We don't want our algorithms sensitive to arbitrary scaling in these different contexts.
Right. We need IR because the scales are different and maybe arbitrary.
But the theorem says if we hold on to IR plus PO and IIH, we lose collective intelligence. We can't effectively combine the incomparable information.
That's the crux. The incomparability makes IR desirable, but IR, along with PO and IIH, prevents true collective learning. It locks us into effectively choosing just one perspective, one environment to optimize for.
Okay, wow. So wrapping our heads around this, what's the main takeaway for you listening to this?
I think the core message is Building AI that learns broadly and fairly across the real world isn't straightforward. There are fundamental trade-offs baked in. Achieving that intuitive goal of collective intelligence might be mathematically impossible without relaxing some principles we thought were essential, like PO, IIH, or IR.
Yeah, it definitely feels like it opens up more questions than answers.
For sure, it pushes us to ask, okay, which of these principles can we afford to relax in a given application? Can we live with violating Pareto optimality sometimes? Or maybe IIH? Or do we need to find clever ways around IR?
And how do we even tackle that informational incomparability? Can we find better ways to translate or compare performance across domains?
That's a huge area for research, and maybe we need totally new frameworks for AI development that acknowledge these limitations from the start.
It feels like a really foundational challenge has been highlighted here.
Absolutely. This points to vital future work, both theoretical and practical, especially for AI in high-stakes areas, healthcare, fairness, distributed systems. The consequences of these trade-offs are very real.
So maybe a final thought to leave everyone with. Perhaps this impossibility isn't just a technical limit for AI.
Go on.
Maybe it reflects something fundamental about intelligence itself, about learning and making decisions in any complex, diverse system. Think about us, humans, society. How hard is it really to weigh different perspectives, compare different kinds of value, and reach a truly collective, optimal decision? Maybe AI is just running into the same wall we do.
That's a really interesting thought. Perhaps it's not just an AI problem, but a universal challenge of navigating a heterogeneous world.